The development of a new product may be a long process. Repeated tests in the field and/or in the lab are needed, and measured results must be evaluated before a new product is completely developed and mature for the market. The question is, how are such measurements made? Let us show you. Most of the tests are made for internal development or project-related purposes, but also external clients highly appreciate the competencies of our professionals, which is why they engage our development specialists to carry out exceptional tests in which we use different measuring techniques. As we saw in the last podcast, numerous tests can also be made in the firing tunnel on our company site. However, seeing that our longest firing tunnel is only 300 meters, we have to go out in the open field for tests and measurements over longer distances. Here, on this particular firing range in a military zone in the Swiss Alps, our developers carry out the most diverse tests several times per year. This gives us the possibility of testing our products over distances from 300 to 1600 meters. For our firing test in the open field, we designed a trailer with a firmly installed gun carriage. This mobile firing stand is of a modular structure that allows us to use the appropriate precision barrel depending on caliber requirements. This high-precision gun carriage relies on the same firing equipment as we use in our indoor firing tunnel, with the difference that we can operate it anywhere in the terrain and in any weather conditions to achieve results matching those in the laboratory. In the firing mode, the trailer should stand on the ground as firmly as possible. The axle can be lowered so that the tires are lifted and the supports move down. This enables maximum precision analogous to our shooting facility at the works. Special measuring equipment is required to analyze all parameters of interest also in the mountains. The electronic hit indication permits us to measure two parameters. On the one hand, the velocity of the particular projectile, and on the other, its point of impact in a virtual target. Both parameters are measured by means of highly sensitive noise detection microphones. We rely on the so-called time difference of arrival principle. Hereby, the time difference is measured between the detection points in time of the individual microphones. Divided by the known distance between the microphones, we get the velocity and point of impact respectively of the particular bullet. This here is our tracking radar. It uses the Doppler effect and allows us to track projectiles as far as approximately 300 meters and read their velocity. The departing projectile reflects radar emissions. The frequency variation between emitted and reflected radar signals results in the velocity. It's exactly the same as on the road when the police zaps cars moving too fast, only that our bullets are much faster underway and smaller. The transmission boxes we developed allow the wireless transmission of any signals in any environment over a range of vision of 16 kilometers, even if no mobile network exists. This means that we can remote operate the equipment also from the firing trailer. For example, the electronic hit indication or the multi-purpose camera. Thanks to this high-resolution multi-purpose camera, we can watch what happens in the target with the factor 20 optical zoom. A steel housing protects the camera from fragments flying around in the target slope. Valuable time is saved because those responsible for the target zone don't have to be on the spot after every shot to indicate the hits. Our experts use ruggedized laptops to display all data of relevance to the system in any weather. These devices have been developed for use under adverse conditions, be it hot or cold, in the sunshine, rain, or snow. They always work. As in the firing tunnel, the gun carriage is aligned as far as possible in the direction of the target. A telescopic sight is provided for fine adjustment. Two adjustment wheels serve to adapt the vertical and horizontal settings of the table. Seeing that we fire at different distances, we use basic ballistic data calculated in advance. This chart shows the projectile flight path for different test firing distances. The shooting person uses the data to correctly set the telescopic sight to the desired firing distance. While one half of the team installs the high-precision gun carriage, the other half sets up the target. The biggest possible target is needed to test fire newly developed products at such long distances. Yes, it is true that not even our own developments hit hole in hole right from the start, especially in a case like this one at a distance of 1,100 meters. Apart from this, such simple cardboard targets are always useful for precision evaluations, even though the most sophisticated measuring equipment is available to us. Steel targets can also be secured to a stable firing stand so that bullets can be tested for their penetration capabilities. The multi-purpose camera now permits to permanently monitor in high definition what happens at the target location. Bullet entry holes can be investigated conveniently. Moreover, the target slope can be inspected from the gun carriage by means of the spotting scope. Here we test various projectile structures in respect of their penetration capacity in steel. Although a first assessment by camera is possible, the performance must also be checked on the spot. Of top priority here are not only the shape and size of the penetration holes, but also deposits occurring on the side. This bullet structure was an absolute success. Planned during these testing days is also a test which should enlighten us on the burning up behavior of propellant in order to guarantee the highest possible safety in the production plants. What would happen if the powder caught fire? Would there be an explosive reaction, or would it simply burn up? How hot would it get? This is why our developers built a sort of test house. A bucket containing propellant is placed in the interior and connected via sensors to the measuring device. The course of the temperature is recorded while burning up takes place. It is exactly this type of test which must be made in the open field because nobody knows what the end result looks like. It is now a matter of lighting the ignition fuse and gaining enough distance immediately. The propellant catches fire quickly and then keeps burning a short while until all material is burnt. Burning up occurred as we had hoped. The enormous spreading of the heat, however, surprised even our development experts. The course of the temperature revealed that up to 380 degrees Celsius were measured around the source of the fire. These refined techniques enable us to measure our products and components in respect of their effectiveness, precision, velocity, etc., and all this in-house. We can carry out the most varied tests quickly and flexibly. The results of the measurements permit us to continue our developments and further improve our products.